Hi everyone, my name is Laura Chen. I'm from the University of Toronto, and today I'm presenting the paper GazeRayCursor, facilitating virtual reality target selection by blending gaze and controller raycasting. This work was done during my internship at Meta Reality Labs Research. So first of all, let me show you a little bit of what GazeRayCursor is about. GazeRayCursor is essentially a novel technique that we have designed for 3D object selection that enhances the traditional controller raycasting technique by using the gaze and controller rays for object depth estimation. As we know, object selection is one of the most essential interactions in 3D environments like VR and AR, and raycasting is a technique that's commonly used for pointing and selection tasks in these 3D environments. But one problem with selecting objects in 3D is that objects can be placed at different depths. So, from a user's point of view, some objects may occlude each other. So then, when the ray intersects multiple objects, it becomes ambiguous which object should be selected. And this is a well known problem in the field, and various disambiguation techniques have been proposed. For example, some research introduced a manual mode where a user manipulates some kind of slider to adjust the depth of the ray, and other research have looked into coarse to fine grained disambiguation, which involves first selecting a general area with multiple targets and then decluttering that area. So spreading out the objects in that area, which then makes the target object easier to select. And many of these prior disambiguation techniques have proven to be effective, but they usually introduce some extra refinement steps prior to the selection. So one thing that we noticed is that when selecting objects in 3D environments, our gaze would naturally generally fall upon or near the object that we want to select, right? And so this makes gaze a potentially very natural and even unnoticeable modality that can complement other input modalities in selection and disambiguation tasks. And of course, there has been numerous prior research on gaze-assisted selection. So for example, using gaze together with hand and pinch gestures, or combining gaze with touch input, or aligning both the gaze and hand raise to activate selection. But what's different about our gaze recursor is that we're not using gaze for pre-selection of a target or confirmation of a selection. We really want gaze to act more as an implicit modality in helping with object selection and disambiguation, without the user even noticing that it was there really. So we know that when using only a single controller ray or a single gaze ray for selection, the ray can intersect multiple objects, which makes the selection ambiguous, right? Now, one method to reduce ambiguity would be to use the convergence of the left and right gaze rays, because now that we have two rays, both of these gaze rays would fall on or near the object that we want to select. So then the convergence point of the two gaze rays could be used to estimate the depth of the target. But the problem with this is because the two eyes are very close together, um, as the object is placed farther away from the user's eyes, the two gaze rays can become closer and closer to parallel. And so this led to the idea of gaze ray cursor because we thought, well, what if instead of using the two gaze rays, we use the intersection of the gaze and controller rays to estimate depth and resolve ambiguity? Since the gaze ray and the controller ray are much farther apart, there is a much larger angle that we can use to calculate the intersection. So we came up with two research questions that we wanted to answer. First of all, how accurately can gaze be used to estimate object depth in VR by intersecting the gaze and controller rays? And secondly, how well can this form of depth estimation be used to facilitate target selection in VR? So to answer these questions, we conducted two studies. The purpose of the first study was to explore the different combinations of gaze and controller rays to infer object depth in VR. Now, in 3D space, it's very unlikely for two rays to intersect at exactly the same point. right? So we developed the idea of the projected intersection. Um, Instead of finding the exact intersection point, we find the point on a control array that's closest in distance to a gaze ray. And this is done by calculating the shortest line that connects the two rays in space. And then this projected intersection can then be used to measure the accuracy of an object's estimated depth by comparing the distance between the projected intersection and the hit point on the object. We recruited 12 participants with normal or corrected to normal vision, and then we used an HTC Vive Pro Eye VR head-mounted display, which offers the eye tracking and a laptop to run the study application. So we carried out a simple point and select experiment in VR. In each trial, a white target sphere was rendered at a different depth, size, and angle. And we tested out 25 different depths, 3 different sizes, and 9 different view angles. So the task was basically to select the target by pointing the controller ray at the target while focusing the participant's gaze on or near the target. And the gaze ray was not explicitly shown during the experiment because, as I mentioned, we wanted the gaze to act more as an implicit and natural modality. So once we collected the left gaze, right gaze, and controller ray data from this experiment, in the in the data analysis part, we evaluated 4 depth estimation techniques using different combinations of these rays. For example, here, LGC, which is the left gazing controller method, calculated the projected intersection of the left eye gaze ray and the controller ray. Similarly, RGC used the right gaze and CGC used the combined gaze. ConfGC calculated the midpoint of the shortest line between the left and right gaze rays and then projected this point onto the controller ray. So essentially, ConfGC is similar to existing techniques that estimate depth through eye gaze convergence alone. And we used it as a baseline to compare our other methods to. So we found that ConfGC had significantly larger absolute error than the other techniques. And we also calculated the percentage error of the estimated depth, which is shown in the graph here. And as we can see, the percentage error grew very quickly as the actual depth increased. And basically, depth beyond 4 meters had more than 20% percentage error for all techniques. But the percentage error for closer objects were much lower. Now, this is a zoomed in view of the graph for depth that's less than 4 meters. And so, for example, the percentage error for CGC at 0.5 meters depth was 5.58%. So overall, we found that CGC had the best performance among all the techniques. And so we chose to use CGC as our technique for depth estimation in the second study. Now, at this point, we have established that the combined eye gaze with control array can be used to infer the depth of the target. But questions still remain as to how to best integrate this form of depth estimation into a target selection technique, which is our second research question. This brings us to study 2, where we designed and evaluated our selection technique, GazeRayCursor. So the GazeRayCursor actually had 2 variations, which are the GazeRayCursor Auto and GazeRayCursor Semi. We compared these 2 variations against a baseline technique called RayCursor, which is a very effective technique recently developed by Balut and his collaborators. So let me go into each of the 3 selection techniques in more detail. In RayCursor, the baseline, the default behavior is raycasting. So when the controller ray intersects one or more objects, the intersected object that's closest to the user is highlighted. This RayCursor technique also supports a manual adjustment mode. And what this means is that when the user's thumb touches the controller's touchpad, a red cursor appears and moves along the controller ray in accordance with the user's thumb swipes. In GazeRayCursor Auto, Gaze is used in combination with the control array to disambiguate between objects, and this was directly derived from the CGC method from study 1. So remember that we calculate the projected intersection between the gaze and control arrays to infer object depth, right? Um, when the control array intersects one or more objects, the object with a hit point that's closest to the projected intersection is highlighted. And for each object that the control array passes through, we display a red flashing circle at the hit point to help focus the user's gaze on the object. And finally, for GazeRayCursor Semi, by default, it behaves exactly like GazeRayCursor Auto, but it has the additional menu adjustment option that's the same as in RayCursor. And the purpose of including this semi-auto technique in the study was so that we can look into how often participants would use the menu mode to disambiguate between objects if they were given the choice. So in the second study, again, we recruited 12 participants, and none of the participants from study 1 took part in study 2. And also the same apparatus from study 1 was used in study 2. Now, because the goal of study 2 was to see how well our techniques could resolve ambiguity in target selection, we have created a highly dense environment to basically maximize the likelihood of disambiguation being needed during each trial. And this dense environment consisted of 4 layers of uniformly distributed grids of spheres. In each trial, there was one dark blue target, while the rest of the spheres were distractor objects. And the task was basically to correctly select the target and move on to the next trial. So each participant went through this target selection experiment with all 3 techniques counterbalanced, and here's what we found. In terms of the task completion time, GazeRayCursor Auto and GazeRayCursor Semi basically achieved significantly faster task completion times compared to RayCursor in all 4 target depth layers. In fact, GazeRayCursor Auto decreased selection time by 45% compared to RayCursor. There was actually no significant difference between the two gaze recursor variations, and this is quite a promising result because it shows that maybe the menu adjustment option is not needed for the gaze recursor to just perform well time-wise. We were also interested in seeing how often participants would use the menu mode to disambiguate between objects. And we found that on average, GazeRayCursor Semi reduced menu depth adjustments by about tenfold compared to RayCursor. But to be fair, the high menu mode trigger rate for RayCursor was to be expected since targets behind the first layer were heavily occluded and RayCursor's default raycasting behavior highlighted the closest object to the participant. So we would need to manually move the cursor behind the distractors blocking the target. But on the other hand, the manual mode was triggered much less often for gaze recursor semi, which again is an indication that the GazeRayCursor technique by itself, without manual adjustments, was often sufficient for selecting the target. Our research, of course, had limitations that should be discussed. So first of all, some participants reported that sometimes pressing on the trigger button for selection caused shaking because of the force that's required to press the button, which could lead to false selections. And this phenomenon is actually a well-known side effect of using spatially tracked input devices, and it's called the Heisenberg effect of spatial interaction. Secondly, our studies were conducted in abstract environments. And even though the participants found GazeRayCursor easy to use, we think further work is needed to explore this technique within real VR application scenarios. And last but not least, it's important to note that we tested GazeRayCursor against the baseline RayCursor in a very dense, close-range environment because the goal was to see how well GazeRayCursor could resolve target selection ambiguity. But at farther depth or less dense environments, The baseline RayCursor may also reach better performance than how it performed in our study 2 setup. So the results from our study should not be overgeneralized to more sparse target environments. In summary, we found the combined gaze and controller method to achieve a significantly lower error rate in depth estimation compared to the baseline that relied solely on gaze convergence. We also found that both the auto and semi-auto variations of GazeRayCursor demonstrated faster selection times compared to RayCursor in a dense environment, and selection times between the two variations were similar, regardless of whether the manual mode was available or not. Nevertheless, GazeRayCursor Semi may still be the best technique going forward, since the manual mode would give users more control when gaze cannot precisely pinpoint objects that are farther away. And so it takes the best of both worlds. And that concludes my presentation. Thank you.